right, now we've looked at discrete time stability for Lyapunov. What about linear time invariant systems? How is it going to look for linear time invariant systems? So here we have our linear time invariant system, x of t plus 1. So f of x is equal to ax. We consider this candidate Lyapunov function. So again, it's a quadratic candidate function. And instead of looking at the derivative along the system trajectory, we look at the difference along the system trajectory. So delta v is equal to v of x of t plus 1 minus v of x of t. So this is v of x of t plus 1. Here's v of x of t. X of t plus 1 is equal to ax of t transposed. The transpose is x transpose a transpose. And so each of these two terms has x transpose on the left, x on the right. I can factor those out, and I get this. So if I call this matrix now minus q, x transpose minus qx, okay, like we've seen before, then I have this. V of x of t is equal to x transpose px. Delta v of x of t is equal to minus x transpose qx. So the idea is we want p to be positive definite, q to be negative definite. So in which case, this is actually given by this equation. We actually have an equation called the discrete time Lyapunov equation. So this is this function v is a Lyapunov function if p is positive definite and q is positive definite. Okay, so we have that condition. We can also look at it this way. I have what's called a linear matrix equality. That is, this is a function of p, and it's linear in p. It's also a function of q. It's linear in q. Or my stability problem can be looked at in terms of a linear matrix inequality. A transpose pa minus p must be negative definite. That is, since if this is equal to minus q and q is positive definite, then this quantity must be negative definite. This must be positive definite. Sometimes it's easier to solve problems if you can set them up as inequalities as opposed to equalities. Now, it turns out that if our system is indeed stable, then our Lyapunov equation has a closed form solution. So for a given Q matrix, I can solve it this way. P is equal to this infinite summation from 0. It's like, whoa, where did that come from? That's crazy. It's the infinite summation of Q from K2 goes to infinity to, from 0 to infinity, of A to the power K transpose Q A to the power K. And so this must be required, that is, the spectral radius of A must be less than 1. If that's the case, then A to the power K goes to 0 as K goes to infinity, and so this infinite summation actually, as a summation, converges. So we actually have convergence in that case. Now, we can actually go through and show and prove, and so I'll actually show that in the proofs video, that if the spectral radius of A is strictly less than 1 and Q is positive definite, then P must be positive definite. Okay, so we have this property that holds. And actually, there are a number of related properties that hold, but this is the most important one. If A is of spectral radius less than 1 and the Q is positive, then P is positive definite. Okay, so it's kind of working backwards. Usually we think in terms of, we start with the V, which is the Lyapunov candidate. We get the derivative or difference along the system trajectory, which gives us the Q. So we start with the P, we end up with the Q, and we look at the Q. In this case, we're actually starting with the Q, looking for the P, and getting the P, and evaluating it that way. So it's kind of a different way of looking at it. So as I mentioned, we can actually prove a number of related things. Actually, I have two things: the stability of A and the definiteness of either P or Q. And if I'm given either of those, I can prove the other. So if this is less than 1, Q is positive definite, then P must be positive definite. If the spectral radius of A is less than 1 and P is positive definite, I can go through and show that Q must be positive definite, and so forth. Alternately, if both P is positive definite and Q is positive definite, then the spectral radius must be less than 1. So I have the three properties, and if I'm given any two, I can prove the third. Okay, so this is actually the Lyapunov stability issue, this one here. So that one's fairly straightforward to prove. And we go through and actually show in depth the proof of this one. We could alternately prove this one. Okay, but that's what we're looking at here. So this is the discrete time Lyapunov equation, and it appears for linear time invariant systems. Now it turns out that we're going to actually be able to modify this equation a little bit and actually incorporate other properties. But this is the basic discrete time Lyapunov equation. We're going to come back later, actually, we're going to look at Q, and we're going to modify Q. We're going to choose a particular Q that is associated with either the input or the output of our system, and we're going to look at stability related to other properties like controllability and observability. And so it's interesting how those kinds of things are going to pop out of the Lyapunov equation. But this is the linear time invariant discrete time Lyapunov stability.